Okay, Dr. C number 2 from homework number 10. Now, as a physicist, I really don't like to have just magic formulas that we don't understand where they came from. So I'm trying hard this semester to really justify everything you see on a fundamental basis. So even Newton's law, F equals ma, when we first introduced it, it was just, no, here's an experimental fact, accept it. But later I tried to explain it, or hopefully did explain it to you, based on just the symmetry of space and conservation of momentum from which you could derive Newton's laws. But at that time, we also, or even before then, I guess after that, we had introduced this idea of air drag being 1/2 CD, the density of air, times the cross-sectional area of the object times the velocity squared at which it's moving through a fluid. And I just said, well, you have to accept this for now, but I'll be able to explain it later. Well, now is later. Now that we've dealt with collisions, you have enough information at your disposal to understand where most of these terms come from. We can't really get the 1/2 right because motion through a fluid like air is really complicated with all sorts of things going on. But you can get an appreciation for the most important aspects of this just based on simple collisions. So what I say in part A is let's take a cylindrical object moving through the air. It doesn't have to be cylindrical. I could have made it a cube or something else, but a cylinder is convenient. So we have a cylindrical object moving through the air at speed v, and it has a cross-sectional area A on its face. Imagine a flat face for now. And it's going to push its way through air and feel the force of air drag as a result. Okay, and a way to appreciate the effect of this motion through the air is to think about not just individual air molecules. We could do that, but then that wouldn't be in terms of the density of air. But to think of that in any given time, this cylinder is going to encounter a block of air, which will also be a cylinder of cross-sectional area A and length L. These two A's are the same. Okay, my drawing isn't perfect. And so in a given time, it'll encounter a cylinder of air of cross-sectional area A, and the length of that cylinder will just be the velocity times whatever time interval you pick. Okay, just our standard distance equals velocity times times formula. And so it encounters this cylinder of air and has to push it out of the way to continue moving. And again, we won't worry about the details of how it pushes it out of the way because that gets complicated, but just treat this as another rigid body, if you like, although we know it's not very rigid. So that's a huge assumption. Okay, so this cylinder has a length, L equals Vt. It's going to have a volume, okay, its cross-sectional area times its length, or AVT. And it's going to have a mass equals the density times the volume, or just the density times AVT. That's actually all you were asked for in the first part. What's the mass of this block of air that in the time t the cylinder is going to have to push out of the way somehow? Okay, so we've got that. Now part B says, okay, instead of worrying about the individual collisions with air, just think of it as a collision with a block of air. And we know this block of air is going to be much lighter than any cylinder that we're going to be worried about. And we have to then ask, well, okay, what's the effect of that collision? What's the expected velocity of this air after the collision? The velocity of the cylinder is not going to be affected much with any small bit of air that it pushes through. Okay, now, over time, this velocity will be diminished. We know that's what air drag does. But if we pick a short time interval in a short little section of air, short little length of air, then we wouldn't expect this to slow down much. Okay, and so what would we expect to see is that, okay, we have a collision between a massive object, a big M, moving at the velocity v, and a little m that's just sitting there at rest. And you know from our collisions, the special cases for elastic collisions, okay, and we'll assume this is elastic, because you don't expect the air to lose much speed on average when you do this, or much energy. You don't expect the system to lose much energy. But also I just tell you to assume an elastic collision. Okay, what's the final speed, or what's the final, what's the expected velocity of the air after the collision, and what's the expected speed? Well, if this is moving at speed v and this is initially at rest, We know after the collision this continues to move at speed v, but this little m moves off at final velocity 2v. Okay, and we showed that in the lecture notes several times. So the expected velocity of the air, okay, after the collision is just 2v. And that's what you were asked. What's the final momentum of the block of air? Well, the final momentum of the block of air will also be the change in momentum of the air, by the way. P final minus P naught, and that's 0. The final momentum of the block of the air will be its mass times its velocity, equals m air, v final air, or rho a vt, that's the mass we have from up above, times 2v, and I just rewrote that as p final equals 2 rho a v squared. As you see, we have a v squared coming in there now. That's good because we know we expect that in our formula times the time. So that's the final momentum. That's part D. Part C says, okay, the force on the air is the same as the force on the cylinder. This is an action-reaction pair. The forces on each other. Okay, so now we can write the drag force. Just label it as what it is. The drag force, okay, is just the change in momentum, delta P over delta T, okay, or dP dt if you like, because we're talking about short time intervals, so that this is a small block of air. So the speed isn't changing much over a short time interval. So that means just take the time derivative of this expression, but that's easy because t appears there only as t. So this is 2 rho a v squared. And that's the force of the block or the cylinder on the air, but it's the same as the force of the air on the cylinder. Now, if you like, you could put a negative sign in front because the force on the cylinder is in the negative direction, but we're just after the magnitudes here, so I'm not going to worry about that. That leaves us to just part D. Okay. Oh, by the way, this is probably a good time to step back and say, hey, this is the formula we're predicting the force of drag. The correct formula is 1/2 CD rho a v squared. We've got the a, we've got the v squared, we've got the density of air, right? We haven't considered the CD, and instead of a half, we have a 2. So those are the things you might worry about at this point. And part D says, okay, let's worry about CD. Okay, so in the analysis so far, we had a flat surface for this. Okay, and CD for a cube, I think it's in the book, but CD for something that's flat is on the order of 1. Okay, and let's just accept that. And because what the question asks, well, what would happen if our cylinder, instead of having a, this way, so it's the same direction, instead of having a flat surface, what if it had a streamlined surface? Okay, and let's assume, okay, let me draw a cross section of this. It's moving with velocity v, so a cross section might look like this. And we'll assume that this angle is 45 degrees. Okay. And what we're trying to do is simulate a sphere or a hemispherical end, because we know that for a hemisphere, CD drops to a half, but that's going to be a little difficult to set up as an integral and talk about all the changes in motion. But if it's a 45-degree angle, then when an air molecule, we can look at from the rest frame of the cone, when an air molecule comes in and hits it, we expect it to bounce off at a 90-degree angle. Okay. Angle in equals angle out. Okay, and we've actually done some of this in 2D collisions. And from the reference frame of the cylinder, the same thing's going to happen. Okay, you're going to deflect it by 90 degrees instead of having it bounce in and straight back out, as we had to do for a flat end. Okay, so if you have a deflection of 45 degrees instead of 180 degrees, what does that do to our expression for the force of drag? Well, we're going to think about that, and the change in momentum for 45 degrees is 1/2 the change in momentum in the x direction for a flat surface. Okay, and we could take that into account in our formula by saying, okay, that CD for a flat should be 1/2 CD, or I'm sorry, CD for a 45 degrees is about 1/2 CD for a sphere, for a flat surface. Okay, that's about what we see in the correct formula. For a sphere, CD is about 0.5, and for a flat surface, it's about 1/2. So we can also understand that on the basis of just basic collisions between the air molecules in this cone. Now you might ask, well, what happens? Aren't we giving the air some momentum in the negative y direction? That's true, but we're also giving it some of it momentum in the plus y direction. So by symmetry, these two things will cancel out. So with our formula, now we have again the factor of 2 instead of 1/2, but we can understand where the CD comes in, why you have to worry about the shape. The shape just takes into account the change in momentum. And so, for example, if you had a really streamlined tip on this, then the air molecules coming in would bounce out at almost the same angle, or I mean almost not at all, really. And so you wouldn't be deflecting them at all. And so if you're not deflecting them at all, then you're not changing the momentum at all. And so that's why you might say CD gets small for streamlining, just on the basis of the change in momentum for the air molecules over the surface of the object that's moving through them. So hopefully you feel like you have some appreciation for where most of these factors come from, except for the 1/2, which I haven't tried to explain. That's it.